Dear learners, I believe you've been following through with the teaching on rotational motion, rigid body, moment of inertia. Today we are looking at conservation of angular momentum. Conservation of angular momentum, and we consider two examples. So, conservation of angular momentum. What that means is that in a body undergoing angular momentum, there is conservation if there is no additional force applied to that system. So when a system undergoes angular momentum, then it is conserved. A rotating body with no external force acting on it conserves its angular momentum. That is, the initial angular momentum will be equal to the final angular momentum. That is, the angular momentum is unchanged. Okay, it's unchanged. And the practical application is a skater. The skating sports. Let me show that you see that rolling rotating image. You have ice skaters and they are exercise. That sport illustrates what happens when the body is rotating. You will see that for the skater, when the arm is spread out, angular momentum, that's probably the initial angular momentum, L of its I, and at a point, while still spinning, the hand is retracted closer to the body, and you have the final angular momentum. At both instances, the angular momentum, is the same, as this they are conserved. And remember that angular momentum is the product of the moment of inertia of the body and the angular velocity of the body. So what does that mean? That means because the angular momentum is constant, then what could vary interchangeably is either the moment of inertia or the angular velocity. Remember that moment of inertia is a function of size, mass, and size, or distance of the body, of the mass distribution with respect to the axis of rotation. So if you check the initial angular momentum, when the skater, the arm is spread out, however, that at that point, the radius of gyration of that lady will be higher. Okay, the radius of gyration will be higher for the lady. This first lady, the first image on the left hand side. So I, moment of inertia, will be larger. The same lady, the mass is not changing. Okay, so but because her arm is spread out, then the moment of inertia will be higher than the second image where the hand is retracted, is closer to the body, and at that point the radius of gyration is lower. That is why you have a lower moment of inertia. However, as the moment of inertia decreases, as the lady retracts her hand and the moment of inertia decreases, then our spinning velocity, the angular velocity, increases. Okay, so it compensates. However, the angular momentum at both instances remain the same. Okay, the angular momentum at both instances remain the same, and that's what is illustrated here. And that's what that means. What does that mean? That means for in conservation of angular momentum, I will be inversely proportional to omega. That is, as moment of inertia of the body increases, for conserved angular momentum of a body in rotation or rotational motion, then as the moment of inertia of that body increases, then the angular velocity decreases, and vice versa. That is, as moment of inertia decreases, angular velocity increases. Okay, so that principle, the principle of conservation of angular momentum, it states that the total angular momentum about an axis of rotation for a system is constant rather, provided that no balanced external torque acts on it. Okay, the total angular momentum about an axis of rotation for a system is constant. You have a body system of particles, no body system of particles. So everybody is made up of particles. Okay, so we have a system of particles, you have a body. The angular momentum of that body about an axis is constant. Provided that there is no external torque, that the turning of the body, the rotation of the body is not influenced by any external torque. Okay, so that's what it means. L is always a constant, that is, I omega is always a constant. That's why we said L starts with I is equal to L starts with F. The angular momentum at one instant will be equal to the angular momentum at another instant. And from there, you have that expression. Okay? So, and likewise, for such a body too, the energy is also conserved. That is, the rotational kinetic energy is constant at any instance throughout that spinning, as long as there is no unbalanced external torque acting on the body as it rotates about its axis, then the kinetic energy is also conserved. That is also I omega squared is the same. However, as I said, when I is decreasing, omega will increase and vice versa. And so the individual values of I and omega will change at several instances. However, the kinetic energy itself is constant. Okay? And again, we have the summary now. Again, I just want to be familiar with all these formulas because they are what you need to master them, be familiar with them. Because when questions, you have to attempt questions and you write out the parameters provided in the questions, then it is your familiarity with these expressions that determine how fast or determines how we'll be able to pick the right tool to solve the question. Okay, so I want you to be very familiar. Go through all the expressions we've obtained so far and get familiar with them. That's one of the secrets for success in this type of courses, and generally in physics generally, familiarity with the formulas, the expressions. Okay, so we have torque, we have the expression for torque, then for work done, we know that. Then for rotational kinetic energy, we just consider that again. And also for power, we know for power too. And we can move on and on. Then, which include moment of inertia, where K is meters of gyration, angular momentum, which is also, remember, we've considered this before now, the expression. And also, we have the conservation of angular momentum, what we just considered now. And we can, from there, work with several problems that we come across. Okay? So let's see this example. Example E1. A flywheel of moment of inertia 95 kilogram meter square rotates about its axis with an angular velocity of 60 radian per second. Now, the axis of a stationary gear wheel made up of a quasar with its shaft of moment of inertia 5 kilogram meter square is then linked to the rotating flywheel by friction clutch, causing the two wheels to rotate with the same angular velocity. Determine the angular momentum of the flywheel before the gear wheel is linked to it. Then the angular velocity when we now have both the flywheel and the gear attached. Okay. Okay. So now let me just show you some certain things that you need to know. Now remember, the flywheel has its moment of inertia, so it's rotating, and the moment of inertia is 95 kilogram meter square. So call it I for the flywheel. Let me call it I. I don't want to call it F because I've used IF as final moment of inertia. So for flywheel, let me call it I flywheel. Okay, I flywheel or I fly F W flywheel. Okay, and that flywheel has an angular velocity of 60 radian per second. So omega of the flywheel. Okay, angular velocity of the flywheel. So alone, that means we can determine the moment of angular momentum of the flywheel. So first one is known, the angular momentum of the flywheel before the gear wheel is linked to it. Okay, so you can obtain it by multiplying those two, I and omega, for the flywheel. Now, the question now further says that the axis of a stationary gear wheel. Now, another wheel, but a gear wheel is stationary. That means it has no velocity. Okay, it's not spinning. However, the moment of inertia, if it spins, it will have a moment of inertia of 9 or 5 kilogram meter square. So for the gear wheel, I, this 5 kilogram meter square is the GW. Okay, gear wheel. And you link the gear wheel to the flywheel with the help of a clutch. Okay, the gear wheel has a shaft, and you link it with the flywheel by a friction clutch. So 4 things there: the flywheel, the gear wheel, the shaft, and the clutch. 4 things. 4 things. So normally, because the clutch will have its mass, the shaft will have its mass, the flywheel will have its mass, the gear wheel will have its mass, then they should have, and when they rotate, when they are fused together and they rotate, they should have their moment of inertia. However, the question now says the moment of inertia of the clutch and the shaft are negligible. What does that mean? That is, maybe the mass of the clutch and the shaft is so small, or the radius of the direction is so small that it does not have any significant effect on the momentum when the flywheel is linked together with the gear wheel. So it's assumed to be negligible, so it's assumed to be 0. Okay, so that simplifies our work. So in this case now, we're only working with the moment of inertia, the flywheel, and that of the gear wheel for the second part. Okay, so if the two wheels now rotate, then what will be the angular momentum? Sorry, what will be the angular velocity? That's the second part. When the two rotate now, what will be the angular velocity? Okay, And let's see. You see that the first part, the angular momentum is obtained for the flywheel, which is 95 kilogram meter squared and 60 radian per second. They're in standard units. Don't worry, you multiply it to it and you have your answer, which is 5,700 kilogram meter squared per second. Okay? Now the second part. Remember I said that the shaft and the clutch have negligible moment of inertia, so you disregard their eyes. So we just work with the two other wheels, the flywheel and the gear wheel. Initially, at one point, the flywheel is rotating alone. Now it is now rotating joined together with the gear wheel. Okay, so that's what it is. The flywheel by itself, then the flywheel now together with the gear wheel. What would that give us? So we have the I for the flywheel alone and omega for the flywheel. That's 95 times 60. Now, for the because the two wheels on the other side now, the two wheels are joined together, we have the same angular velocity. However, the total moment of inertia will now be a function of the two wheels. So you sum up the individual moment of inertia, that's for that of the flywheel, that of the gear wheel together, then multiply by omega. Okay, so you have that. So you have 5,700 kilogram meters square, then it's equal to 95 plus 5, which will be 100. So this will be 100. So the total amount of inertia now, when you have both joined together, it's 100 kilogram meter square. Then you have to determine the angular velocity. So from there, make omega subject of formula, and the answer will be 57 radian per second. So for emphasis, look at it. When the flywheel is alone, I is 95 kilogram. Don't mind me, I'm using my mouse to attempt writing. Okay, when you have the flywheel alone, and at the angular velocity is 60 radians per second. But now look at it. Joining the gear wheel to it has increased the, do you get it? Moment of inertia. It is now 100. With the gear wheel, it is now 100 kilogram meter square. So from the theory, what would we expect? We expect that as long as the angular momentum is conserved, then you expect that the angular velocity will decrease. Do you get it? It will decrease. There's inverse relationship between the two when the momentum is conserved, angular momentum is conserved. So and that's why we have 57 radians per second. Straight away. Okay, let's see. An ice skater is preparing for a jump in which she will rotate while in the air. When she's on the ground, her arms are extended. Her moment of inertia is 2.2 kilogram meter squared, and she is spinning at 0.31 revolution per second. She launches herself into the air at a speed of 12.6 meter per second at an angle of 45 degrees above the horizontal. At the moment she leaves the ground, she contracts her arms, and this contraction takes a negligible time, so it's unnoticeable. A fast, very, very perfect, very good ice skater. And contracting her arms now changes her moment of inertia. No, that will happen. It changes it. So now, how many revolutions can she complete? Can she complete rather? Can she complete while airborne? How many revolutions can she complete while airborne? And we have to take G as 9.8. That's our acceleration with gravity as 9.8 meter per second square. So again, arms extended, then amount of inertia is 2.2 kilogram meter square, and our angular velocity is 0.31 revolution per second. Now I can convert that to radians per second by just saying one revolution is 2 pi radians. So just multiply 0.31 times 2 pi. We have radian per second because the rate is already revolution per second. So second is already there. Just multiply 0.31 by 2 pi. However, I won't want to convert to radian per second because I'm to obtain my answer in revolutions. I want to have my answer in revolution. Okay, revolution. So I don't need to. I can just leave it as revolution per seconds. Okay. She launches herself into the air at a speed of 12.6 meters per second at an angle 45. It now contracts. So contracting the hands now reduces the size. You get it now? And that means our radius of gyration will reduce. That means the moment of inertia will reduce. So from 2.2 kg meters squared, the I is now 0.62 kg meters squared. So you expect that angular velocity will probably do what? By the time I decreases, the angular velocity will do what? Will increase. Just trying to emphasize what I've explained prior to this slide. So I've used this image to describe it to also aid in understanding. Look at that. This is the ice skater. At this point, it's 2.2 kilogram meter squared. All right. Then, as she was spinning on the ground, she tried to launch herself to the air, and she did that with a speed of 12.6. That's V, meters per second. 12.6 meters per second. At an angle theta. Angle R. This was 5 degrees. It's not theta. We use theta to represent the rotation, rotation. That's theta, rotation. Okay. But the angle at which she launches herself was 5 degrees above the horizontal. Okay. So what do you think will happen? Because of gravity, she will get to a point. Showing herself, she will get to a point, a peak point in here. Then because of gravity, she will start coming down again. Okay? So that's what happens. You see her at this point, the middle image there, then she starts coming down again. Now, she contracts her arms and that changes her level of inertia and she lands. Okay? So we have to determine the revolution. And that means, number one, why the revolution she completed while she was able. That is, the revolution she completed just when she left the ground and just before she returned back to the ground. Do you get it? And we can obtain that. How? We also need some other things. What do we need? We need, because we are doing velocity, we need to calculate the distance it took. But remember that angular, remember that the revolution is equal to what? This. Angular displacement is equal to angular velocity times time. And to obtain time, then we need to know the distance covered. If you know the distance covered while she was airborne, then you can know the time because we know the velocity with which she went. However, the velocity is at an angle. So the velocity to which she covered this distance, you can know it by resolving this F towards the horizontal, this V rather, towards the horizontal. Okay, we resolve V towards the horizontal, we can obtain, and with T, then we can obtain S. However, we need to obtain S, we also need to bring in the principle of projectile. No, the lady now is like a projectile, launching up at an angle to the horizontal, the projectile. So we use that to obtain our S. Then we resolve our v towards the horizontal, then to obtain the velocity, then we obtain our t from there. From there, we are good to go. Okay, so yes, the angle is given 45 degrees. The velocity at which the ice skater launches herself is also given as 12.6 meters per second. However, to determine the revolution, the angular distance covered by the rotating ice skater while airborne, then s is the distance between the point she leaves the ground and the point she returns. Okay, so to obtain our v, we are working with vs, the horizontal component of the velocity. So v here is 12.6 meters per second. Then we obtain v, and for our angle 45 degrees here, we obtain it. If the angle is here 45 degrees, our vs will be v cos 45 degrees. Okay, our vy will be v sin. Recall vector resolution. We've done that. Okay, so let's see the solution. Solution. Again, the moment of inertia of the ice skater, 2.2 kilogram meter squared, and our angular velocity 0.31 revolution per second, which you can do. Told you we can do it, but it's not necessary actually. Okay, you can convert it to radian per second, but it's not necessary because we are to do our answer. The question is how many revolutions. Okay, and the velocity at which she launched herself at 45 degrees to horizontal is 12.6 meters per second. And while airborne, the moment of inertia decreases to 0.62 kilogram meter squared. Calculate the final angular velocity. The one we have, because the angle of momentum is conserved. By the time I changes, then omega will change. Okay, so straight away, let's say it. Li equal to Lf, and you obtain the final angular velocity by making our omega f subject of formula. From there, if you substitute, for give omega f is this, then you have I substitute I, then omega substitute I over I substitute f. Okay, so you have that I substitute I, the moment of inertia at the initial stage 2.2, angular velocity 0.3, and moment of inertia while here airborne 0.62. So if you substitute and you compute, you have 1.1 revolution per second. So we now have omega f, that is the final angular velocity to 1.1 revolution per second. That is sorted. Okay, we need to now obtain our t. Remember again that what we want to obtain is number of revolution, which is omega t. We have our omega, we need to obtain our t, and that's the complex part. I want you to pay attention again. Okay, duration or time for the ice skater to be airborne, t is the distance covered while airborne, horizontal distance covered by airborne over the horizontal velocity. Do you get it? Horizontal distance covered by airborne over the horizontal velocity. Okay, that's how to do that. And we can get the horizontal distance using the formula for range. Remember, recall projectile. And the formula for range is v squared sine the angle at which the projectile is launched. V is the velocity the projectile is launched here. Then the angle psi is the velocity, the angle at which the projectile is launched with respect to the horizontal, and g is a constant associated to gravity. And you substitute the v, which is 12.6, and your angle, which is 45 degrees, then you have the horizontal distance covered, which is 16.2 meters. 16.2 meters. Now, you can also obtain the time now. That means the horizontal distance s and the s component, horizontal component of the v. Now, v is the velocity which is 12.6. I told you that the horizontal component will be v cos theta. So just substitute v cos theta where we have v substitute x. V cos theta where we have v substitute s, because that's the horizontal component of v. So the t is equal to S over B cos the angle, and you put your expression 16.2 meters over, that's your S, then the velocity 12.62 meter per second, and cos of the angle to which the data is launched is equal to the resultant, that's 45. So you have cos 45, and you substitute, you have t to be 1.818 seconds. It took the escalator 1.818 seconds to be airborne. The time it took her to lift herself off the ground and return to the ground is just 1.818 seconds. And with that known, now you can now obtain the number of revolutions you obtain while airborne, which is now, as I said, our number of revolutions, the angular displacement, which is the product of the angular velocity while airborne and the time taken to be airborne. Okay, and multiply that, you have approximately 2 revolutions. So within 1.818 seconds, the ice skater made like 2 complete revolutions. That is the solution. I believe this explanation is clear. If you need clarification again, you can put your comment in the comment section, and I will do my best to attempt responding. Again, please subscribe to this channel so that you can get latest update, because as I receive comments, questions, I will be doing short videos to attend to some of these questions so that you will not miss out. Share this with your colleagues, university, and other universities. Let them also benefit. This is my little contribution to your success. I wish you outstanding success in your academic journey. God bless you.